Dear students, today we'll see what do we mean by digital electronics and logic gates, which is the last part of your semiconductor electronics section. So here, let's start with the topic of digital electronics and logic gates. Now, first we should understand what is digital electronics, and then we'll go to see a few logic gates which are there in your syllabus. Then what do we mean by digital electronics? Now, in electronics, we have basically two categories. So if you speak about electronics, you can have analog and digital. Analog and digital. So here, analog, whenever we represent analog in electrical waveform and we study the waveform looks a continuous. It is a continuous waveform with respect to. So here you have a continuous waveform with respect to time. Similarly, what do we mean by digital means? Instead of having a continuous waveform with respect to time, we'll have discrete waveform. That is, the value will come at regular intervals, not continuously. It will have its value at regular intervals, at a regular time period, at a specific time period, not every time. So it is not continuous. Now, this will be the main difference of representing electronics or electrical waveform in terms of whether they are analog or digital. And then when we saw that the circuits which were built on digital, the systems which were built on digital could eliminate more of the noise, could give good output, could give good transmission, quality of the picture was better, quality of the sound was better as compared to analog. So most of the things, most of the factors of the outcome in the application became very good, very nice. Now, what do we mean by digital electronics? Now, digital electronics will be having certain small systems, small components, small combinations, which are in turn made from analog devices only. We are going to use analog devices only, like your diode, semiconductor diode, which we have studied. This is a symbol of diode. You can have a transistor, BJT transistor, like you can have this type of analog device. These all are analog devices. Now, these devices we will make some combinations of them, we will make a circuit of them, and we will make a new digital electronic component which will give a certain output, a certain combination of inputs. So here, say, if I make the basic digital component, it will be called as gate. Now, this gate will be having either two or three or one or any type of inputs depending upon whatever configuration, whatever you have made it for. And this gate is made out of analog electronics components only. But here I can give certain inputs, and based on the combination of those inputs, I can get the output. I can get the output. So there will be some logic, there will be some reasoning, there will be some logic behind it. And because of that, this circuit, which is made up of analog electronic components, will be called as a gate. And this gate is nothing but it is a circuit made up of basic analog electronic components like diode, transistors, FETs and all. But it will give you a relationship that whenever you have a certain specific input in terms of digital waves, digital information, a specific output you will get. Now here digital information means what? We will not take any analog information. We will take a discrete value. Say this is a discrete value. This is high, low, high, low, high, low. So this is your electrical form of discrete data, discrete value. So this high we will take it as logic 1. This low will take it as logic 0. Again, this high will take it as logic 1. This low will take it as logic 0. In this way, we are having the data. This is known as binary form of system 1 and 0. 1 is nothing but electrically it is approximately 5 volts. 0 is nothing but electrically it is approximately 0 volt. So electrical representation is like this, and we view it like this, we call it like this, and with this 1 and 0 we can make our what you say input data, you can call it. And this input data is nothing but your input information, input message. So it can be information or it can also be called as message. Now, what is our idea is what combination of input I give, depending upon that, a particular output should come out. Say, for example, if I have two input gate and the two inputs are A and B, and the output is say Y. So this is A, this is B, and this is Y. Then in terms of this binary numbers, whatever we have studied, I will give certain combinations. Say for two inputs, I'll give combination like 00, 01, 10, 11. For this combination, I want a certain output. For this combination, I want a certain. For this combination, I want a certain output. For this combination, I want a certain output. So depending upon on that combination, what output you are going to get, you can build different gates. Say for example, in the first combination for 00, I want output as 0. 01, I want output as 1. 10, I want output as 1. 11, I want output as 1. I can build a particular gate. If I want output here as 0, output for this combination as 0. If output for this combination as 0, output for this combination as 1. I can build another type of gate. So depending upon the logic which we want, which can be useful for us, depending on that, using analog electronic components, we can make these digital circuits, which can be in the form of ICs, integrated circuits. And those digital circuits will give you a logical relationship between the input and output. And once we use these circuits, these gates, these circuits, these systems, and everything is digital, that only is the study of digital electronics. So our base of electronics will be analog, but from analog, we are going to transform to digital. So here we'll see the definition of digital electronics. It is a branch of electronics that deals with the study of digital signals, circuits, and the devices used to produce them. Logic gates, logic cameras, digital televisions, smartphones, computer, their memory components, all this, whatever we see in today's life, are all examples of digital devices. Now, only one thing you have to remember is it is a electronic device, digital electronic device. Now, the base of that was analog electronics. The components of analog electronics were used to build up the logic of digital circuits. And then we went on to go on making more and more featured digital devices with which we went on making many applications. And today you see that most of the applications or everything is in digital form. Okay. Then we will come to our specific point, what we want to study, that is gate. Then what is this logic gate? As I've told you earlier, this logic gate will be again built up by your analog electronic devices only, like a transistor, diode, FET and all. And then we are going to use them to make a combinational circuit which will give you a output depending upon the set or the combination of the input. We can also take a feedback from output to input, and we can make a sequential circuit also. All the circuits can be made in digital. Okay, and those circuits will be put in the form of IC, that is integrated circuit, and then we will get this basic logic gates. Okay, so now when we speak about basic logic gates, this comes under combination electronics. So combination means for a certain combination of input, you have to get a particular output. So this is your basic gate. This is a basic component of digital electronics. This is what first we study in digital electronics, along with your binary numbers, that is 1 and 0, which I have shown you how they are represented in electrical form. Now here, first we'll see this definition. A gate is a digital circuit that follows certain logical relationship between the input and output voltages. Therefore, they are generally known as logic gates. Say it is following certain logic relationship between its input and output. So if you draw a gate block diagram, so you can see here, if this is your gate block diagram, and you have certain inputs. Inputs can be 1, 2, 4, anything. So these are certain inputs, and depending upon what inputs you are going to give in terms of binary, whether their inputs are 0, 0, or inputs are 0, 1, or 1, 0, or 1, 1, depending on this combination, a particular output will come out. A particular output will come out. Say for 0, 0, it is 0, for 0, 1, it is 1, for 1, 0, it is 1, for 1, 1, it is 1, anything like this. Because you have built those circuit in that gate in that form that you should get this combination. Okay, like this you can build up any logic. Like this you can build up any logic, and therefore there are few basic logics what we have built, and there are few logic gates which will perform this logic. And these gates, they are generally known as logic gates because they control the flow of information. So whatever input you are giving and whatever output you are getting, it is nothing but it is a flow of information. Now we will go to see what are the basic gates which we are going to study. After this background, I think it becomes easy for you to understand what are these gates. As I've told you, gate will be nothing but a circuit in a form of IC. Gate will be nothing but circuit in a form of IC. IC is integrated circuit. Integrated circuit. Okay, and in that integrated circuit, you are going to use analog electronic components like diodes, BJT, FETs, that is MOS FET, in that CMOS. Okay, all this you're going to use, and by using them, you will make a certain combination of inputs and outputs. So for certain inputs, for a certain combination of input, you will get a particular output. So certain combination of input, you are going to get a particular output. So that will be the function of the gate. Now in this, depending upon your input-output relationship, the input-output relationship will be called as truth table. Truth table. So in this truth table, you are going to represent what are the inputs, and what is the output. Okay, so say if there are two inputs, you can call the inputs as A and B, and the output you can call it as Y. So input, if it is 0, 0, what is the output? If the input is 0, 1, what is the output? If the input is 1, 0, what is the output? If the input is 1, 1, what is the output? So depending upon this, you can have different types of gates. Depending upon the logical relationship between input and output, you can have different types of gates. Now we will see the gates in particular. So here you can see these are some of the important gates. So here you can see you are having the first one as OR gate, and these are the symbols what are shown. Now from these OR, NOR, AND, NAND, XOR, XNOR, buffer, and NOT, from this we will see our basic logic gates what are there. We'll start with the NOT gate, and we will study NOT gate, AND gate, OR gate, NAND gate, NOR gate, XOR gate, XNOR gate. Okay. So these gates, which will be called as basic logic gates. Okay. So these are the symbols what are shown over here. Just a glance for you. Now, one by one, we will see what they are so that you can understand them. So here, the first one shown as logic NOT gate. So can you see this diagram for NOT gate? It is nothing but you're showing a arrow, you're showing a bubble. It is having one input, only one input, and it is having one output. So it is a relationship of one input and one output. So this one input will be, say you have named it as A, and this output you have named it as Q. You can name it any alphabetic. So this is input A, this is output Q. Now in this two combination, what I can have? So here you can see the truth table. This is the input, this is the input, and this is the output. This is the output. Now I will make this combination as, if the input is 0, the output will be 1, and if the input is 1, the output will be 0. Okay, so you read as inverse of A to give the output. So if A is the input, then output Q will be equal to inverse of A, which can be represented like this, which is called as not of A. Okay, so the Boolean expression says that output Y or Q, you can represent it as anyhow, is equal to naught of A. So if you give the input as 1, the output will be 0. It will be the complementary output. If the input is 0, the output will be 1. So this is a complementary output. So a particular combination of circuit, which is called as the gate, which is doing this function, is called as NOT gate. So the name is NOT gate. So NOT gate will be basically having one input and one output. So if input is logic 0, the output is logic 1. If the input is logic 1, the output is logic 0. So in that way, it is going to complement the input. So here you can see this bubble. This bubble is an indication that the output will be inverted one. So this is what is your basic logic gate. So here, this is the symbol of it. This what we have drawn is symbol of it. This is the truth table of it. This is the Boolean expression of it. Okay, and if you want to give a statement, you can read it as inverse of the input which gives the output. Simple definition, simple symbol, a truth table, and expression. Finish. This is what is your logic NOT gate. Then we'll go to one more basic gate, which is called as OR gate. So here you can see the symbol of OR gate. So here if you see, this is the symbol of OR gate. And this symbol will show that whatever inputs you are having, if any of the input is high, the output will be high. Now what does that mean? We'll see. So here you can see this is a symbol first. Here we have drawn OR gate. Okay, OR gate. And this what we have shown is a two input OR gate. So this is one input, this is another input. The first input is A, second input is B, and depending upon this combination of inputs, you are going to get a particular output, specific output Q. Now what will be the combination of inputs? So always we take the combinations as 0, 0, 0, 1, 1, 0, and 1, 1. Okay. Now here these are your inputs and this is your output. Now output Q here in this combination, in this working, in this logic, we want that whenever any of the input is 1, the output should be 1. Otherwise the output will be 0. So if you follow this logic, then in the first combination if you see, both the outputs are 0, nobody is 1. So output is 0. In the second combination you see, A is 1, so the output will be 1. Because if any of the output is high, if any of the input is high, the output will be high. Similarly, in the third combination, B is high, so output is 1. Similarly, in the fourth combination, both the inputs are high, so the output. If you get this type of combination, this type of relationship, then it is a logic OR relationship. Now here, what does the expression say? Expression say that the output Q should be equal to, okay, so it is A or B, which can be written as A plus B form. Okay, so A or B, you are ORing the two inputs. You can have 3 input gate also, you can have 4 input gate also. Okay, but here we'll, for simplicity, we'll take 2 input gate. So you understood this logic here for OR gate. The logic says that there are 2 inputs. Now, from the inputs, if any of the input is high, that is logic 1, the output will be 1. Then we'll go to see another gate, logic AND gate. So here you can see the symbol of logic AND gate. This is what you have to first remember, the symbol. So AND gate looks like this. Okay, so here also we are going to take a 2 input AND gate. So one input will be A, another input will be B, and one output will be Q. And the combination of the inputs, depending upon a certain combinations of input, you are going to get certain outputs. So what will be the combinations? So here we will use a combination that when all the inputs are high, the output will be high. If all the inputs are logic 1, the output will be 1. Otherwise, if any input is 0, the output will be 0 only. Okay, so what does that mean? So we'll see here. In the first case, This B and A are the inputs and Q is the output. In the first case, this 0 0 combination, both are logic 0, the output is 0. In the second combination, you have A as logic 1, B as logic 0, but 0 is there, the output is 0. In the third combination, B is 1 and A is 0, so 0 is there, it is 0. In the fourth combination, you see both A and B are 1. So when all the inputs are high, okay, then the output will be high. So this performance, this combination, this relationship, if you have between the input and output, then it is logically ANDing, logic AND. So the output Q here will be Q is equal to A and with B. Okay, and when you write it in an expression form, you can write it like this, A into B. Okay, so here it is A and B. So if it is like your multiplication only, but here you have to speak it in logical terms. And logically, we say that when both the inputs are high, the output is high, otherwise the output is low. Then we'll go to one more next gate, which is called as NAND gate. Now this NAND gate is nothing but AND gate only. This was your AND gate only. But one extra thing I've shown here is the bubble. That means whatever AND gate was giving output, that output will be inverted and that will be the original output of your NAND. So we know the performance of AND for two input and we know what output we get. So here if you see the Boolean expression Q will be equal to AND output only, but this will be inverted. This will be inverted. Okay. Means what? For AND gate, we know that for 0, 0, the output was 0. But that output 0 now it is inverted and it has become 1 because we are speaking about NAND performance. NAND performance means it is going to give you outputs opposite to that of AND, inverted to that of AND. So similarly, when the input is 0, 1, in AND gate, what was the output? It was 0. But here, the output will become 1. Similarly, when the input is 1, 0, in AND gate, the output was 0. Now, what it will be here? It will be opposite of that, complemented of that, that is 1. If the inputs are 1, 1, in AND gate it was 1. Now here it will be 0. So it will be complemented. Now this complementing, this inverting we have shown here because of this bubble. If you have not put this bubble, then you are representing an AND gate. This was your AND gate. Now you are representing a bubble here. That means output of AND gate will be inverted. Output of AND gate will be inverted. So if you have this type of relationship, it is called as NAND gate. So it is logic NAND gate. Similar will be the case of OR gate. For OR gate, if you put a bubble like this, that is the output of OR gate. If it is inverted, then it will be called as NOR gate. It will be called as NOR gate. Now here also we have shown two inputs A and B and the output will be Q. If the inputs are 0, 0, now in OR gate the output was 0, but in NOR that output will be complemented and the 0 will become 1. Similarly, when the inputs are 0, 1, for OR gate the output was 1, but here it will be complement of that, it will be 0. Similarly, when the inputs are 1, 0, in OR gate the output was 1, but here it will be complemented and the output will be 0. Similarly, for the inputs of 1, 1, the output of OR gate will be 1, but that will be complemented and given as 0. So here you can see this will be the expression for ORing. Actually, here the output Q will be A ORing with B. ORing with B. Okay, so this, sorry, A NORing with B. NORing with B. So here the output will be Q is OR inverted. OR inverted. Okay, so you can read it as A or B gives not Q. So you are going to do NORing. Not and OR is OR plus not you are going to do, which is nothing but NOR. Okay, so here this is going to do your OR and this is going to do your NOT. So the output will be NOR. So then we'll go to see the next logic gate, which is called as logic exclusive OR gate or XOR gate. And the symbol here you can see this is a symbol drawn. So here you can see one more line you're drawing along with the inner symbol. So this is your ORing operation. ORing operation. And here also we are going to show two inputs A and B and one output, that is Q. The expression is given as output is equal to A XOR B. So this is a symbol of XOR. Now what does this combination give? This combination says that if all the inputs are same, then the output will be 0. If the inputs are not same, they are different, then the output will be 1. So here you can see in the first combination when the input are 0, 0, the inputs are same. And in this combination when the inputs are 1, 1, the inputs are same. In that case, the output is 0. In that case, the output is 0. Similarly, when the inputs are different, the output is 1. So if you have this kind of relationship, logic relationship between input and output, then it is called as XOR. Then next we'll go to see XNOR, which will just do opposite of this XOR gate. So here you can see this is also a two input, and here you can see the symbol that this was your XOR gate. This will be your NOT gate. Okay, and this together means that it is XNOR gate. So it has to give you the output which is inverted of XOR gate. So in XOR gate, when both the inputs were same, the output was 0. But that will be inverted here and it will be taken as 1 for XNOR gate. Similarly, here you can see when the inputs are same, the output was 0 for XOR gate. But now it is inverted and you're going to get it is 1. Similarly, when the outputs are different, For XOR gate, the outputs of different means similarly when the inputs are different, the output will be 1 for XOR gate. But in case of XNOR gate, it will be 0. It will be 0. So it will give the opposite or the complemented output of XOR gate, which will be called as XNOR gate. Okay. So here you can see expression, Boolean expression if you see here. So Q is equal to A XOR B, which will be inverted. Now this will be called as XNOR combination. If you write Q is equal to A XOR B, it is XOR combination. But if you want XNOR combination, then it should be Q is equal to A XOR B inverted. Okay. So this is the logic exclusive NOR gate, which will be called as XNOR gate. Okay. Thank you, students.